Hello everyone, welcome to another ME 296 lecture, and this time we're going to not learn anything particularly new. I'm just hoping to kind of build a little bit of intuition about why we do certain things and maybe hopefully clear up a couple of misconceptions. So the first topic I wanted to go over again was the concept of domains and what exactly that means. And then I want to kind of go through transfer functions again a little more clearly and exactly why we use them so much. So domains. A domain is basically a set of units that we're using and then how they interact with whatever system we're examining. And this can be something like converting between feet and meters, which is a conversion between the imperial and the metric system. 1 foot is 0.3048 meters. And they're not equal to each other, but they're related. And sometimes it's easier to talk to someone in terms of feet or meters. If you're talking to an American, you're going to want to say, oh, it's 100 feet that way, versus a European person who grew up in a metric society is going to want to know it's 30 meters that way. Or maybe in America you would say we're 5'10", whereas in Europe you would say something like 0.9 meters, something like that. See, they're related, but they're not equal, and sometimes it's more convenient to use one versus the other. And it's the same thing when we're talking about temperature. There are 3 common temperature measures. There's Kelvin, Celsius, and Fahrenheit, and each of which is its own domain, useful in its own way, and they're all related to each other, but they're not exactly equal to each other. You can't say 1 degree Fahrenheit is equal to 1 degree Celsius. Same with Kelvin. There's conversion formulas that we can use. Okay, so just when we're talking about changing domains in circuits, we're talking about changing from something that is measured one way, and then we're going to analyze it using a different method. Like when we think about circuits, we think in the time domain because that's how our brains work. We think of things occurring in time. But it's not super easy to analyze circuits that way, so we convert them to the Laplace domain or the complex frequency domain, where it's easier to do the math. And it's related to each other, but it's not equal, and sometimes it's useful to solve in one domain versus another. So let's examine the temperature example a little bit. Kelvin is based on absolute zero temperature. 0 Kelvin is the coldest it could possibly be. All thermal motion stops. And we'd want to use this when we're doing like physics problems, because physics constants are often based on Kelvin, like Boltzmann's constant is based on the Kelvin temperature scale. And yeah, you can convert, but it makes equations messy to do so, so you're better off just doing your problem in Kelvin. In Celsius, Celsius is based on the phases of water. 0 degrees Celsius is frozen water, 100 degrees Celsius is boiling water or steam. And certain kinds of chemistry problems or materials problems that deal with phase changes, it's often useful to do these in Celsius. You can convert to Kelvin, but that might make the math a little fuzzy with the other stuff, or you can convert to Fahrenheit, but you're going to have to plug in another function to convert everything back anyway. So you might as well just do it in Celsius. And then Fahrenheit is the oldest temperature method we have, which is based on the freezing point of brine or water with different kinds of salt in it that lowers the freezing temperature, so it's colder than it would be if it was pure water. And this one is intuitively understandable to us as Americans anyway. We still use the Fahrenheit system. If we say that it's 100 degrees, we would know intuitively that we're talking Fahrenheit, and that's pretty hot. But it's not the same as Celsius 100 degrees, where we'd all boil out of our skins and die. So when you're talking to certain people, it's easier to use Fahrenheit. If you're in Europe, use Celsius. If you're solving problems in physics, you use Kelvin. So there's different ways to use these different domains that all measure the same thing, and you can relate them to each other, but sometimes it's easier to use one versus the other. And it's the same thing in circuits. So the one we use in circuits is transfer functions use the Laplace domain, which we get from the time domain. And the time domain is very relatable. Let's say we have some voltage. The total voltage is we have V equals some DC constant V plus some sinusoidal component, or the sine omega t there. Now, we can understand visually in our heads what that looks like, but we can't analyze circuits very well in there. The resistor is fine, but when we look at inductors, the governing equation is L di dt, or the derivative. That's a little harder to visualize. And then we get into capacitive circuits, where the voltage is equal to 1 over C integral of current with respect to time. What does that look like? I mean, we could analyze it and sit and figure it out, but it's hard to understand intuitively. So we convert to the Laplace domain, which is a complex frequency domain where our Laplace variable S is equal to rho plus j omega. And rho is kind of similar to the DC component, or steady state, and omega is our angular frequency, and j is the imaginary variable, or complex. Because we're in engineering now. We're not in physics, so we use j for the imaginary component. And we do this because it's much easier to analyze circuits in the Laplace domain. We went from a derivative when we're looking at inductors to just the value of the inductor times our Laplace variable S. The capacitor just becomes 1 over C times S. We don't have to look at integrals or derivatives. We could ignore that. We see that as S increases, the voltage across an inductor also goes up. And we see as S increases, the voltage across a capacitor goes down. So we could see this right away, intuitively, just with a straight line thing, without having to worry about, oh, if I integrate this form over this much time, what happens? Or what does derivative look like if I do this? We see simply that as we increase our Laplace domain variable, we have a simple relationship to voltage. And just look at an example of these circuits, both identical, one in the time domain, one in the S domain, where the S domain one is on the bottom. The transfer function is the ratio of output to input of the circuit. And the one on top right there, does that look very nice to you? That's the time domain integral of the capacitance, because we have to, we're in the time domain. So our transfer function has an integral over r plus the same integral, horribly messy, and no one would ever want to do that unless they just really like calculus. And it's hard to see what it would look like, because as you change the frequency, you're going to have to change that time that you're integrating for, and you're going to have to do it again for every frequency you're interested in. But if you look down at the Laplace domain, very simple. I walked through how to do this a couple of times to get the Laplace domain transfer function of this particular circuit several times. So if you're confused on how we approached this, go back and watch the lectures on transfer functions and the Laplace domain transfer. I think week 5 and week 4. But you see how the two transfer functions, they both tell us the same information, but one of them is so much easier to work with. And that's why we use different domains. That's why we transmit between the time domain and the Laplace domain. Related, they give us the same information, but one of them is just so much easier to work with right now. And the reason that we use transfer functions is because the transfer function tells us the behavior of a circuit. It tells us what's going to happen if we change our input somehow. If we increase the frequency, decrease the frequency, what's the output going to look like? If we increase our DC component but decrease the angular frequency to component, what happens? We can tell all that from a transfer function. Very straightforward. Now, if we have a specific task that we're looking to solve with some kind of circuit we need to design, then we kind of know what our transfer functions should look like. If we want to have it so that if we have a high frequency, we want to have very little output, we already know what that looks like. So we can design our circuit around that desired behavior to recreate that transfer function. And because circuits are linear systems, there are an infinite number of possible designs that can give us a given transfer function. So the reason a lot of classes, and this one too, starts off with having you create the transfer function from an already created circuit diagram is because you're not going to really know right away how circuit components interact to give us a transfer function. And we're really just trying to show you, oh, the low pass filter transfer function comes from a circuit that looks like this, or the high pass looks like that. So that's why we started off like that. But pretty soon, and in fact, already from the midterm, you're going to start having problems where you're given a transfer function or something that describes the transfer function, and you're going to have to start designing the circuit yourself from that. So let's look at an example of that and what I mean by infinite number of circuit designs that can recreate it. If we have the transfer function up on the top, which is a high pass transfer function, should be pretty familiar to everybody. We want the transfer function graph to look kind of like the plot shown. And we think to ourselves, oh, that looks familiar. Let's just go ahead and make this circuit where we have a resistor and a capacitor in series. We take the voltage output between the resistor and capacitor where the capacitor goes to ground and the source input is hooked up to the resistor. Perfect, that gives us everything we need. I've gone through how to make the transfer function out of this several times already, so I'm not going to do it again, but you should know that the transfer function that we want is given by this circuit. Great, this is a very simple, easy to understand, straightforward circuit. What if someone approaches you with this circuit? Twice as many components. Looks kind of similar, but does it do the same thing? It does. It does exactly the same thing. Because those two resistors right there, you add them together, they're in series to create one equivalent resistance. Capacitors in parallel, they give you a simple sum of their capacitance because they're in parallel. And then the voltage output in the same place above the capacitance between the resistor. So even though the circuit in orange is more complicated, it does the exact same thing as that circuit over there. The only important part is that the resistor values are equivalent and the capacitor values are equivalent. There's no difference. You could design either one when given the transfer function plot shown above. Which one would you prefer? And that's kind of the intuition we're trying to build when we show you simple circuits and stuff. So let's do a little recap. Domains. Domains are things that are related to each other, but they're not equal, and we can convert from one domain to the other. We can convert from Celsius to Fahrenheit. We can convert between the time domain and the Laplace domain, and they are related to each other, and they give us much the same information, but sometimes it's easier to talk or solve problems in one domain versus another. And we use them to simplify solving our problems. Transfer functions describe the behavior of a circuit. And this is very important because we need to solve problems, which means we need to know some kind of idea of what our circuit looks like when it's in action, what it's doing. And the transfer function tells us exactly that. And we can get them from an existing circuit. Like say you're a spy and you stole a circuit from someone, you could recreate what that circuit's doing. Or if you need a specific task done, you can create the transfer function and then design the circuit from the transfer function. And finally, there's an infinite number of ways to build any circuit for any behavior. Remember, it's a linear system, so a linear system means we can have as much or as little complexity as we want, as long as the sum of all of our parts comes out to what we need it to come out to. Generally, we're going to aim for simplicity, because it does no good to design something with 80 million parts if your boss is going to come at you later and be like, we only have money for 3. So design things for simplicity, especially for this class, and they tend also to be easier to troubleshoot if something goes wrong. So yeah, try not to be too complex when you're solving problems in this class from now on, because I'm going to be asking a lot more design questions. I'm going to give you behaviors like a transfer function and then ask you to design a circuit or control system around it that works for that. And it's going to be open-ended. And I realize that there's not a lot of classes that ask for this kind of open-ended problem solving. It's usually just here's a circuit, analyze it, or here's an equation, solve it. But we're going to start moving into a little more complex upper division level problem solving techniques. All right. So I hope that helped. Please feel free to ask me any questions through either our class discussion board or send me an email. And I'll try to help you out. Try to build a little more intuition about why we do things the way we do. All right. Thank you.